Today we're going to talk about the geothermal energy. And to begin with, I would like to share with you a statistic released by IEA, which is the International Energy Agency. It was released 8 months ago. They're estimating that there's going to be an increase in the energy demand. And this increase of energy is going to be fulfilled by mostly renewables. And 15% of this increase will be supplied through the geothermal energy power plants from now, like 2025 until 2050. So the topic we are discussing today is not less than the future of the energy, or it's going to be like a major part of the future energy sector. And also, currently, the geothermal energy system, energy sector is actually $1.2 billion industry. And it is $1.2 billion industry. And by 2050, it's predicted to be about $2.2 trillion industry. So to begin with, I would like to ask you a question. We have fossil fuels and we have the nuclear power plants. The main question is, why do we extract fossil fuel? Why do we create nuclear fusion? Why do we do that? And how we generate electricity after all? Anybody can answer this question, please? Any contributors?
When Igor was having a presentation, we discussed part of this topic. So, Igor, do you want to join?
Did you mention me? Excuse me.
Yes. Abdi was having a question. And
yeah.
During your presentation, we touched the topic of energy from nuclear power plants. Maybe you have opinion on the topic. And oil. Maybe Abdi, can you repeat the question?
Yeah, I can answer the question. I'm just trying to have some interaction. That's it.
No, can you repeat the question?
So we extract fossil fuel. We also have nuclear fusion. Why do we do that, and how this concept works to generate electricity? So what's the relation between fossil fuel and electricity?
So basically, we use the fossil fuels to generate the electricity, but transfer the chemical energy, which is located inside of the chemical bonds, to produce the different type of the energy, so the electricity. So we use, for example, the turbines, which we spin, for example, when we turn the coil or gas to produce the mechanical work, and by using the generators, we generate the electrical work, electricity.
Exactly. So this is the main idea. We use fossil fuels, we use nuclear fusion, so we can create heat that heats up the water and turns into steam. And this water that we have, we pump it inside the turbines, we rotate the turbines, and the generators will rotate eventually, and then we're gonna have electricity generated. The same concept applies for the geothermal energy, but the source of heat is not fuel, it is not nuclear fusion, but rather it is the internal earth heat. But before we dive into the geothermal models, we need to understand how this internal heat is actually behaving. So first of all, we have the core, as you can find it at the center of the earth. This core is the inner core, and it is very hot, and also it is pressurized. So I have a question here. This core is about 6,000 Celsius as degrees for the temperature. But why it is not melting? Why it's not liquid? Why, for example, it's not gas? Why is it in solid state? Anybody can answer this?
Probably because the pressure is super high there, so it doesn't let it become as a liquid. And it's the center of the gravity of the planet. So the gravity force there, probably doesn't let it spread away.
Exactly. So when you have extremely high pressure, it is too hard for the matter, for example, the minerals that we have inside, to turn into liquid state or to turn into steam because they are pressurized and they can escape and expand. So eventually, after this high pressure and this high temperature, these minerals try to decay and produce radiation. And this radiation goes through these layers until it reaches the crust. And then this creates kind of temperature gradient. So as you go deeper, closer to the core, you're going to have higher temperature. And this gradient is about 25 Celsius degrees per kilometer. But this is like the mean value. It depends on the geographical location. For example, if you are closer to volcanic activities, or if you are closer to divergent boundary tectonic plates, where plates are getting away from each other or they are submerging each other, then you're gonna have different temperature gradients. So as the mantile, which is the biggest layer of Earth, gets closer to the crust and gets closer to the surface, you're gonna have higher temperature gradient. That makes sense. And also we need to understand that for Earth, we have like kind of good balance between the heat generated and also the density. So if the heat generated was extremely high and the density was lower, we're gonna have something similar to the sun. So if you see at the sun, the core is 6 million Kelvin as degrees. But however, if you go outside this core, going to, for example, the photosphere or the chromosphere, we're gonna have lower temperatures. But somehow when you reach the corona, which is like the atmosphere of the sun, if we compare it to our system, it reaches 1 million Kelvin. So if the temperature gets too high for Earth, we're gonna have unbearable living conditions. The atmosphere will be too high because its density is actually low. So I just wanted to like give you some understanding about the geothermal energy, the internal energy of Earth and how it works. Now, going to our system. We have hydrothermal, binary, enhanced geothermal system, and super hot geothermal system. If you can see this picture, you find out that I actually organized them in some sequence. Can anybody like explain why did I organize them in this way? Like why one go before the other one? All right, so I can let you know. Basically, the top, which is the hydrothermal, it is the shallower or the shallowest depth that we need to dig inside Earth so we can actually use this model. The binary system is the same thing. As you go deeper, you need to have different models. Shallower one, hydrothermal, then binary, then enhanced, then super hot. It is the deepest depth that we require. And also before we start, I want you guys to review some of the questions. Just give me a second. Yes, we have some questions here for discussion. What makes drilling challenging? I can answer these questions at the end. What are the economics about the geothermal energy? We're gonna discuss it, and then we might have like sort of discussion also with some of our friends, especially the ones who study economics in their degrees. And also we're gonna discuss how far did Bulgaria reach. I did my own research, but I would like to also hear from our Bulgarian friends who might have a better vision about this topic related to Bulgaria. So going to hydrothermal project, we have three requirements: the heat source, the reservoir rock, and the cap rock. So the heat source is something very rare to happen actually, because again we have shallow depth, and if you are at the top, you're gonna have lower temperatures. So you need to have either magma or hot rocks that are basically like created due to the, again, tectonic boundaries or the volcanic activities. And we have the reservoir rock. This reservoir needs to be porous and permeable. Does anybody understand what porous mean?
Porous, yes, there is porous cement that is helping cities to not get flooded, because the water goes through this cement. So it is permeable or porous cement. This is how I relate.
Yeah, that's actually really good. Porous, it means that there is space, so it can store water, as our friend said. And permeable, it means that the rock has the ability to actually transport this fluid through it. So it has pathways where the fluid can go through. And also we need to have cab rock. And if you see, the cab rock should be impermeable seal. So this cab rock happens to be at the top. Then we have the reservoir rock. And why is it at the top? Is because the water and the fluids usually are lower in density, right? So they usually try to get out of the system. They usually try to get to the upper layers due to the density difference. So the cab rock should be impermeable and doesn't allow this water to go away and to just be wasted. So this system has several advantages. The first one is it is very reliable. It works 24-hour, 7 days a week. It's not like the solar panels or the wind turbines that is constrained by the environmental conditions. And also it is very high efficient, because in these systems, they are like a sky raining gold, because you have shallow depth, you have very hot rock, you have also reservoir that happens to be nature, like naturally occurring reservoirs. You have also cab rock. So again, it is like gift from nature. And also we have disadvantages. It is location dependent. So these systems, you cannot find them anywhere. They are too rare to find. Some specific places like Iceland, Nevada in America, Indonesia, and also Italy. So the hydrothermal system has two major models. The vapor dominated, the rarest model that you can find in any geothermal system. So the temperature ranges is extremely high. It means that the water inside, when it gets up, it is actually steam. This conveys and transports enormous amount of energy. And another thing, when you are in shallower depth and when you have a reservoir at this shallower depth, these reservoirs has high capacity because the pressure is low. Again, pressure inside Earth is like water. So if you, for example, are at like 10 meters deep inside water, you're gonna feel with some pressure, right? But if you go to 100 meters, you cannot survive. You will be crushed probably. So the same idea happens with Earth. If you are at shallow depth, then these spaces between the rocks, they cannot be closed because there is not enough pressure to close these spaces. And also this adds up and creates pathways where these reservoirs can naturally be regenerated. So you take water outside and this water gonna be regenerated naturally. So we don't need to have some injection or so on. And this power plant is in Japan. And this one here is the first geothermal power plant. It was made in 1911. It is in Italy. And again, the main problem is these systems are not cannot be commercially efficient. And that's why geothermal energy is occupying a margin lower than 1% of the total energy consumption. Because look at it, this 10% of single city need of electricity, very low, right? But again, because it is gifted and it is like almost free resource of energy, they bought the power plants and they invested into these vapor dominated hydrothermal systems. And we have the liquid dominated, the same idea, but it happens to be in deeper depths. So you have higher pressure and the water, instead of being steam inside the rock itself, it will turn into steam when it gets outside the rock. And this creates some complexities because, you know, as we discussed in the fluid mechanics webinar, I think it was like 1 month ago, we discovered that if you have some state change inside your fluid, this is gonna cause lots of complexity as we discussed previously. So these power plants happen to be in Iceland, Philippines, and also Kenya. And in Iceland, it is pretty unique. They took advantage of their location. And now 2/3 of the energy that they consume are due to the geothermal energy. And 25% of electricity that they use are also due to the geothermal energy. So now moving to the binary system. The binary system is very basic. It is like a upgraded version of the hardware thermal system. But we have a trouble here. Not every place in the world has the capacity of having naturally occurring reservoirs and these reservoirs that can regenerate itself. So we're gonna need to inject the water that we take again inside the rock to heat it and move more like again and again and again inside the loop. So here's the illustration. As you can find, we have production well. It gets the water from the reservoir. It moves it inside a radiator. So this radiator like transfers the energy from water to a secondary fluid. And this secondary fluid has low boiling point. So we don't need water here to be steam or like to be supercritical. This water can be liquid with enough energy and enough temperature just to make the secondary fluid boils and goes inside the turbine and then start generating electricity. And here's another thing. We also have a good benefit of this radiator system because when you get water from inside, especially when like lower depths, which are about 2.5 to 3.5 kilometers in deep inside the earth, some chemistry changes happens. Like you have, for example, limestone, and this limestone might dissolve inside the water. And if you get this water from the bottom and you pump it, even though if it is steam, it's gonna affect your turbine a lot and gonna cause some erosions. So that's why we use secondary fluid. Again, because sometimes the water cannot be in a steam condition, and also to minimize the erosion and the tearing that might occur when you have some mineral particles coming from the water that's inside and hits the turbines. So again, use moderate temperatures, heat secondary fluid vaporizes, closed loop geothermal water working with the fluid. They never mix. This is very effective system. Now we have also some designs for the binary geothermal systems. We have the classic one, the one we just discussed. You dig deep inside, 2.5 kilometers. Then you hit like a reservoir. And this reservoir, as we stated, cannot be regenerated. We also have geopressurized brines like basalts. So sometimes when you go again deep inside, some reservoirs are highly pressurized, and this gives you like kind of flexibility. We're gonna understand how this creates flexibility in the next model, but it creates flexibility for the demand. Like for example, you need sometimes to supply higher energy, you need sometimes to supply lower energy. So this gives you the ability to adjust the production rates. Now, we also have the co-produced floats from oil and gas. Again, we said that we drill about 2.5 to 3.5 kilometers. And most of oil and gas wells that we drill are actually in this scale. So, do you think that we only produce oil and gas? Can anybody answer this?
Well, it is written in the slides that
Okay. Yeah, my bad. So we generally don't produce only oil and gas. We also produce water. And this water can reach percentage of like 20%, sometimes 40%. So instead of just wasting this water, we can have a sidetrack and move it to a geothermal power plant and generate energy. And lastly, we have these systems, industrial waste heat. So here we don't use the heat out of the industrial regions. Instead, we are using a concept that was used in the industrial, in the factories and the industrial integration. So we have something called ammonia water working fluid. So instead of using isobutane, we can use this water mixed with ammonia. I'm just giving you this example so we can understand that geothermal energy is not just like about geothermal stuff, but also it can be related to different industries. And we're gonna discover something really interesting of how these sectors are integrated together in this system. Okay, so we have the enhanced geothermal systems. As you can see at the picture, we have like one well, again, injection well, and we have production well. But in these enhanced geothermal systems, we are going to dig deeper inside the earth. And why do we do that? Like, why don't we just go like binary system 2.5 to 3.5 and that's it? Well, because if you look at here, these are the energy potential at 2,000 meters, the shallow depths that we discussed before, like the hydrothermal power plants. As you can see, only Iceland, some parts of Japan, Indonesia, Kenya, and Nevada in the United States, they have these good potentials of geothermal production. So not all countries can have these potentials at these shallow depths. Even if you go deeper, like to 4,000, as you can see here, also not all places are covered. Like some region like India, it literally has no geothermal potential at 4,000 meters. However, if you go much deeper, till 7,000 meters, almost everywhere has this potential. And that's why we have these different systems, and that's why we change our depths according to the geographical conditions. So what happens in EGS? EGS, we're gonna drill deep, like between 3.5 to 5 kilometers. But here's the catch. We cannot have naturally occurring reservoirs. And it is due to two main reasons. First is the pressure and temperature. So if we have high pressure, as we stated again, if we have any possible pores or spaces between these rocks, the bearing amount of pressure gonna close these spaces, and you cannot have basically a reservoir. And also there is another contributor here, which is temperature. If we have higher temperatures, the rock gonna expand, and this also creates higher pressure upon the rocks and closes the pore spaces between these rocks. So we're gonna artificially create our own reservoir, and we have two approaches for this. The first approach is utilizing the temperature factor. So we're gonna inject water inside. The water is cool, and it's gonna be mixed with the rock, and it's gonna take some time, so it cools down the rock, and the rock can shrink, and like instead of being expanded, it's gonna shrink, and then we're gonna have more pathways, and we have like reservoir potential. However, this method is not very efficient because you cannot have like huge reservoir potential. You just have very limited potential. But it is efficient in matters of that you don't need to like consume lots of money to pump the water in high pressure, because the other approach uses the two factors, the pressure and the temperature. So we're gonna pump water in very high pressure so that any spaces between the rocks that is closed due to the pressure of the internal pressure of Earth, we're gonna open them, we're gonna force them to stay out intact by applying high pressure by the water that we pump. But this consumes lots of money. But again, it creates good amount of reservoir potential. And also this water should be cool because we also want to take advantage of the temperature. We're gonna decrease temperature of the rock, it's gonna shrink and open more pore spaces. And that's how the enhanced geothermal system works, basically. We have here an example. Like it usually happens in multi-wells. Like in first phase, it is usually only one well for production, one well for injection. However, like in commercialized designs, we need to have multiple wells. And can anybody would like give us one of the reasons of why we use multi-wells instead of only one injection and one production well. Okay, so the very obvious reason is we need to take advantage of the reservoir that we are drilling. We need to have higher production rates. And there is another thing. Basically, assume that you have a balloon and you are breathing inside this balloon and you're trying to expand it. If you stop breathing or if you stop giving it some air, it's gonna shrink, right? The same thing happens in these reservoirs. If you stop pumping water with high pressure and you just take your water out from the bottom and you stop pressurizing these rock matrices, they're gonna shrink, they're gonna expand again, and they're gonna close these spaces that you already opened. And it is like irreversible process. So any advances that you had, any stimulations that you have made, any planning, all of them will just be destroyed. That's why we need to have multi-wells. So for example, if we need to maintain or to have some maintenance in one of these wells, we still have this potential of pumping water without new troubles. There is a company called Ivor. I hope I'm pronouncing it correct. They are trying to have another idea. Instead of artificially creating reservoirs, which by the way has also something interesting, they can create something called induced seismics. So for example, we always are headed by these seismics, which are waves. Some of them might be high, so we're gonna have an earthquake. But these reservoirs that we create artificially induce these seismics and gives us higher risks of having earthquakes. And that actually happened in 2017 in South Korea when they had 5.5 magnitude earthquake due to the geothermal plants that used EGS systems. Anyways, so Ivor had another approach. We're gonna create a radiator inside the earth, but this is very expensive. Like this project only gonna cost them $3 million, but it is very effective in the long term because it gives you the ability to adjust the demand. So again, in the artificially used reservoirs, we need to pump water all time. All time we are spending money, we are pumping water, we have the same rate of production. But here, we don't need to do that at all. If we need to minimize the production, we can just minimize it easily. If we want to get it higher, we can increase it. So there is no headaches regarding the production rates, regarding the maintenance, regarding all these troubles. But again, it is very expensive and it needs technical advances. It's not an easy thing. And most importantly, it needs research, development, and to gather information. Now we have another system, which is the super hot geothermal systems. We're going deeper now. So if we look here, we have geothermal systems where fluid in the reservoir, which is supercritical condition. So what is the supercritical condition? Here is the diagram that shows you the phases. I want to ask you, what do we need in terms of pressure and temperature so we can reach supercritical water? Anybody can answer that?
Like we need a high pressure and a high temperature.
Yes, that's very true. So we need high pressure and we need high temperature. And that's why we drill so deep inside. We go deeper, so we're gonna have pressure and we're gonna also have temperature. And why we need to have this supercritical? Because like the amount of energy that the fluid transfers to the turbines is enormously high. Like it can be from 5 to 10 times higher than a conventional geothermal plant. That's why we are trying to reach these supercritical phases. But again, these systems need development, they need testing. And as you can notice, for example, we are trying to reach these potentials through Iceland. Why Iceland? because to reach this supercritical state, we only need to dig deep as 4.5 kilometers. But in any other place, it might take 6, 7, or even 10 kilometers deep. And again, if you reach these depths, the main trouble here is drilling. Can anybody estimate like how much does drilling cost from the initial capital of a geothermal project? Just only drilling the borehole, how much money does it take, like in percentage?
80%?
That's close. It's a bit lower. It is 50%. And again, this is like 50% only for one single well, for single borehole. That is like 8-inch in diameter. So why is that? Because drilling like needs lots of time. It needs also equipment. And by the way, like conventional drilling can take up like 1/8, like 1/8 of the time that you spend on the rig is only utilized for drilling. You have 7/8 of your time only utilized for other operations that are not related to drilling. Like, for example, taking the string up, changing the bit, and casing, cementing. And also, if you go that deep, you're going to have the risks of melting. So you need to have good materials, and you need to have research and development. So we need to understand how these reservoirs are occurring, because we said that if you have high pressure, it is too hard to have reservoirs, right? But these reservoirs occur due to the magma. So the magma flows, and the magma is basically rock that was melted, and this rock also contains some fluid like water and so on. So this water is under very high pressure, and it tries to escape this magma. So sometimes it goes through the rock matrices and stays inside. How do we know it is under? It has high pressure? Because if you are this deep, it means that this fluid is undergoing enormous amount of pressure, but however, it stays intact and stays inside the reservoir. So we drill, we try to reach these reservoirs, but we still have some troubles. Like, as we stated, the drilling troubles, the melting, the research and development. You need to understand the geology and lithology of your own country, for example, of your own region. And there is an interesting thing that can happen as well, which is chemistry changes. So inside these depths, and due to the magma content, that due to the magma, like this fluid is actually was under, like surrounded by magma, so it has high silica content. So now assume we're gonna take out this fluid from inside in supercritical situation. What do you think these silica can cause to your turbines? It's gonna cause lots of tearing. And also, if you're gonna have this secondary fluid stuff, which is not really like your goal here, because you need to take this water under this high pressure. So just let's assume that you just want to utilize the temperature, no need for the pressure. You're also gonna have lots of tearing along the casings, along the pipes. Like you have the well surface is actually steel. It's made out of casing pipes, very strong pipes. So these tearings will cause you to expend more time, more maintenance cost, and so on. And that's why these systems are under development. And like for 50 years, geothermal energy didn't have any sort of like progress. But we have something interesting by this company, Twice. This company uses very interesting way to drill, which is geothermal. So we are not gonna have any direct impact with the rock. Instead, we're gonna vaporize it. So the rock gonna turn into vapor, and we're gonna take this vapor by nitrogen. It is like complex process, but anyways, it's very innovative development, and they are very promising. They state that, for example, after the 3 kilometer range, like we're gonna drill 3 kilometers conventionally with like regular pits, but afterwards we are going to have these systems implemented. And can you imagine, like, their optimized scale or result is like 1 kilometer of drilling will take about 41 days. That's like the scale of which these projects takes lots of time. And since these like projects takes lots of time, the IRR value, like the revenue that you're gonna have, will be low. So, for example, if you have a fossil fuel company, you want to have 20% to 25% of the capita as revenue per year. But unfortunately, in renewable energy resources, this percent decreases a lot. For example, solar panels and also the wind turbines, this percentage is between 5% to 10%. But this company claims that by implementing their systems and by 2030, the cost, like again, we said that drilling takes about 50% of the cost. So we're going to minimize these drilling costs, and also we're going to minimize the time. So the revenue that you're going to have will be in this range, which is high, and like might convince the fossil fuel companies to invest more money, to invest more time and potentials into this industry by 2030. And also, there is another thing related to geothermal energy. When we talk about EGS systems, or when we talk about the AGS or SGS, this problem is we are having very high megawatt hour cost. That's, for example, like renewables, like wind turbines, solar panels. These cost maybe $20 per megawatt hour to $30. But as minimum for these geothermal systems, it is $68 per megawatt hour. So this also creates lots of constraints. And again, for example, if you are a fossil company, you're not going to invest so much money into this industry. It is unproven yet. It is under development. And also fossil fuel occupies 80% margin of the energy consumption that we use today. So anyways, this is a illustration of the Geotron that they use. And this Geotron is actually creates nuclear fusion. So it can create enormous amount of temperature, of heat that gonna melt down the rock. And here how it works, as you can see in this picture. Also, they face lots of troubles as well. For example, they say if we have water infiltration inside, this is gonna be very consuming for both energy and also time, because you need to vaporize this water so that you can get access to the rock. So they are trying to implement some solutions for these issues. And here's the cost breakdown. Geotron itself is 1.1 million. The waveguides, which are like the pipe lines that we use for the drilling strength in conventional drillings, is 2.3 million. But we have the rig structure itself is 8, and compressors and pumps, because again, we need to take the rock from inside. We need to pump nitrogen, and we need also to clean this nitrogen from the rock particles. We're gonna put it inside water, and then we need to also, the water is gonna be heated. Then we need to put it down, and lots of trouble is gonna happen. So this is gonna take another $7.5 million. In total, it is $19 million. But it is actually good, because if you want to reach 6 kilometers of drilling in conventional way, it's gonna cost you about $27 to $30 million. Just for the scale, it actually increases exponentially with the depth. For example, if you want to reach 3 kilometer depth as your borehole, this is gonna cost you only $6 million. Anyways, so I would like to hear if anyone of you has some questions related to this company. I'm just discussing it briefly with you. There are, of course, more details, like, for example, they found the problem that some rocks have the same temperature for melting, but somehow they don't melt at the same time. Why is that? Because some rocks may have quartz, and this quartz reflects some of these wavelengths. some of these waves, microwaves, and this makes you like in trouble sometimes. Instead, for example, I was planning that I'm gonna finish this project in 100 days. It's gonna take me 120, something like that. And of course, some of the troubles that they have is the rig itself. So you need to have kind of friendly environment for these machinery. You need to have UFD units, and also these Zeritron works on very high voltage. That's why we have UFD units. You need to have generators. Also, you need to have cooling systems for these Zeritrons. And yeah, this company is still under under research and development. However, in last month, I think the 22nd of June, they have reached a milestone of drilling 1 meters, like in actual field. So that's kind of promising. And also they have a contract that they should start generating electricity due to their like SGS model by using this type of drilling. By 2030, they're gonna generate electricity. That's their claims. So let's see if any of you has some questions. Then we gonna discuss the economics.
I have a question, but it's not regarding this company, but regarding the whole system. Like, I want to ask you which materials we use for the tubes, in the sense that doesn't it start to melt when it's already like close to the earth core, or when it's in this direction? Like,
Okay, that's a really good question. So unfortunately, I'm not like a material engineering student. I forgot to introduce myself. I'm a petroleum and natural gas student. So I'm not really aware of the types of materials. I can give you some costs, for example, like how much does it cost? Like what are the properties they must have? Because by the way, it's not only about the heat and temperature that's inside the rock. There's also about the pressure. So just assume that you have 6 kilometers depth, and you are putting, for example, a pipe. Underneath it, there's a pipe. Underneath it, there's a pipe. So the pipe at the bottom is actually very pressurized due to the top, right? So you need to have some specific properties, and I'm not really aware of them right now, unfortunately. But thank you for the question.
thank you for your answer.
I'm also not so acquainted about the materials, but I have heard that for some drills they're using diamonds or like diamond heads. So maybe for the deeper drilling, maybe they use diamond heads.
Yeah,
But
that's
needs
yeah.
to be checked.
That's very true. Like for example, when you drill basalt, or when you drill basalt, the basalt is very tough rock. So you're gonna have to have a strong bed. And also, even though you are using diamonds, by some time, due to temperature and also due to the pressure and to the hardness of the rock, you're gonna need to change this string frequently as you go deeper. Because again, as you go deeper, the density gets higher, and the rock gets harder. And this consumes the time. And that's why we stated that 1/8 of the time is only effective drilling. 7/8 left are for the time that you take this string, like this whole string of pipes. It might be 6 kilometers, might be 5 kilometers. You take it away, put them aside, change the bit, and then put it again inside. So that takes lots of time. Yeah. Does anybody has more questions? I would appreciate. Like we are discussing, we are not answering. All right, so that's fine. Now we want to discuss some like context regarding this industry. So what countries do you think has the highest potential to have this industry flowering and enhancing more and more? What type of countries? Besides
Like the Iceland?
Yeah, Iceland. And also, there is another consideration, by the way. Like, do you think that countries that already has oil and gas heritage might be more ready or readier to have geothermal industry? Do you think they are ready more than other countries?
I think that maybe because they have the infrastructure for extracting oil, and they didn't finish their reservoirs. Maybe maybe they're thinking about investing in that kind of infrastructure for and renewables in general in future, also because of the Kyoto Protocol and some other international documents that are binding them. But I haven't heard that they're so interested. I don't know. Like, this is my opinion. This is what I know. You can tell more.
Yeah. So basically, one of the major factors that can help us to develop geothermal systems by the upcoming years is that your country should has kind of heritage or industry that already existed, like oil and gas, so that you can have the engineers and most importantly, the information. So one of the major troubles now is that lots of countries that didn't have oil before, they didn't have research and development. They don't really understand their own geology, right? And if they want to have geothermal systems in their own countries, they need to import this technology from other countries, right? That's why, for example, country like United States is one of the major contributors because of funding. Funding is very crucial now. And also because of that, the country itself is the highest producer of oil right now. And they understand their own geology better than anybody else, better than any other country that might also understand their own geology. And that's, these charts can explain a lot, for example. So we have the next generation geothermal technology investments. And we have the oil and gas skills and expertise and also careers. So for example, if you have EGS system, only 24% of this system are required to be like any other engineers other than like the engineers that work in oil and gas. Only 24%, like the power plants and transmissions. However, 7%, for example, for surface facilities, like rigs, like pipelines, and so on. This might be also related to chemical engineers. And 57% for drilling and well completions. So I hope you got the idea. If your country doesn't have the ability, if your country doesn't have this technical privilege, so they can like have their own geothermal systems, they are not gonna progress. If anybody wants to add something, I would appreciate it. By the way, do you see the chart?
Yeah, with the blue circles.
Yeah. That's good. All right. So it just shows you that only small margin of these systems are required to have different expertise other than oil and gas. All right. We have also an interesting chart here. So this shows you that most of the wells that we produce in oil and gas are between 2 to 3 and also 3 to 4. So that shows you that the only way to have this industry succeeding is by initiating and tries to encourage the fossil fuel companies like Chevron, Shell, these operative companies to go and invest into this industry. And that's why CAOS is working. It's funded by the government. So it can create like kind of safe investment environment for these companies, so they also go and invest money into this industry. And by the way, this shows you a very important thing. If the next generation, like the only thing that we bet on is the next generation geothermal systems. If the next generation doesn't success, then there is no light for the geothermal system. If you look closely, the light color shows the graph without the next generation geothermals. By the way, it is by 2050. You see the contribution, it is extremely low. But if you have the next generation geothermal enhancement, we're gonna have about 15%. All right. And for example, these are the costs of conventional drilling. So the shale means like the oil and gas wells that you drill. This is the cost of them. It's extremely high and goes exponentially with the depth. So for 4,000 meters, which is 4 kilometers, it's between 8 and 10 millions of dollars. And this goes just exponentially. If it reaches 6, it's going to be 30. And this shows you the potentials of the geothermal. Like this is the potential amount of energy that can be produced if the geothermal system works for 20 years worldwide. So if we have, for example, 7 to 8 kilometer depth, we're gonna have, for example, 6 to 400 terawatt of electricity. But if we go lower, the potential it's getting lower and lower. And here are the very interesting thing. If you look again closely enough, the major contributor here is United States and also China. China, because it has lots of funding. United States, because it knows its geology. And also, by the way, China has some experimental wells that they drilled. I think they have drilled a 12-kilometer deep borehole just to conduct experiments. Also, we have India, have South Asia, and we have the rest of the world, as you can see. So, last of all, we're gonna discuss the Bulgarian experience with the geothermal. We have several wells scattered around the country, and also we have some naturally occurring thermal springs that can be used as hydrothermal. But again, hydrothermal projects are not very commercialized. We just use them because it's kind of a gift that you utilize, but you cannot depend on them. That's why you need to have deep exploration wells to understand the lithology, to understand also the geology of your country. And here is this citation. We have 840 water resources with high temperatures. That's really good. But the main trouble, again, if you read the second paragraph, the main issue with hydrothermal, with geothermal, is that planning and analyzing needs to be advanced. So they had the support of the World Bank, provide knowledge, to provide experience, to provide information and analysis for the government to take the correct decisions. Also, Bulgaria is enhancing something really interesting. So they are investing $1.8 million euros, so they can develop the geothermal plant for one of their industrial regions. It is very promising, and hopefully these systems can be implemented not only in Bulgaria but all around the world. That's for all. Here it shows you like we don't really need to have only steam or to have supercritical state. These supercritical states are used for electricity production. But sometimes you can just have like warm water or high temperature water to do other stuff. Like, for example, you can do farming, you can do greenhouse, you can do fish processing, you can do industrial processing and drying. Lots of operations can be done only due to the geothermal energy. That's for all. Thank you very much. And lastly, I would like to show this graph. we have technicians, right? We need to have expertise. We need to have people who have knowledge, who can work, who have experience. So again, oil and gas industry, if it is enhanced and progressing in your own country, it gives you very smooth transition to geothermal energy. Because as you can see in this picture, like for example, Saudi Arabia, they are having lots of graduates per year. United States, Netherlands, because Netherlands has the company Shell, which is operative company, and also Turkey. Turkey is the fourth country to have geothermal, like geothermal energy production. So, anyways, thank you for your listening. I hope you enjoyed, and I hope you understood, and both of us like created something useful in discussing.
Yeah, I wanted to ask about Bulgaria. Yes, we're more focused on shallow geothermal energy, and there are projects with European funding in some cities. They're using the hot mineral water. It is combined with the central heating system, and it is used in governmental buildings or kindergartens. So this is something that I understood. I learned a while ago, and I think it's quite interesting. Especially for the Bulgarians, I don't know, maybe for the foreigners as well, but for the Bulgarians, we're thinking that we're not developing so well, that things are not happening here, but it is like things are happening. Actually, also in Varna, like we have hot mineral water, and actually there were protests because there was a swimming pool that was on accessible prices that was managed by the municipality, and on that place they built building. They sold the land together with the hot mineral water source, and this building, it will be heated with this hot mineral water, and of course, like there are pools inside, etc. Like to connect it more to us, like to our community, the topic. This is what I want to share.
Yeah, that's the good part of geothermal energy. You can use it for several applications: heating, fishing, farming, lots of applications, not only electricity. So yeah, I'm glad to hear that like you're protesting to like be more connected to their own natural resources. That's really good. And thank you for this intervention. I would like to ask if anybody has feedback or again a topic that we can discuss. I would appreciate.
So I want to thank you for the presentation. It was really interesting. I also learned some new things for me. I just have a small question. What is your personal feeling about the future of this type of the energy? Do you think it will be just a supplement, like it's mostly now, or it will take a bigger share in as a part of the renewables in the future?
Yeah. So I think probably there is good potential. I mean, again, the main trouble is drilling. I'm not saying like I'm an expert, but I have sort of understanding of drilling. I already had my internship in drilling field, by the way. So if drilling in haze, we have lower costs. And again, horizontal drilling, which is used by EVOR, gets enhanced as well. We're gonna have very high potential for the geothermal energy. But the main problem is lots of countries, they have their own like power plants and they work in a specific way. Like for example, Indonesia. So in Indonesia, they have they don't use fossil fuel. I think they use coal for their own power plants. On the same time, Indonesia has very good geothermal potential, but they are not taking advantage of it. Because the main trouble here is you're gonna invest money after 10 years, after 15 years, you're gonna have progress. And some countries may not be able or they don't have like this enough space. So they're gonna put lots of money and they can wait several years to get profit. Some countries are constrained by their own economical situations. So the funding is very limited. And they just depend on like the conventional ways of generating electricity, like fossil fuel, like coal. And that's unfortunately true because currently 80% of our energy of electricity is produced by fossil fuels. So this just provides you like, the easier solution. Like it is somebody who is trying to buy a meal. So he has two options. Either he goes cook his meal, gets the ingredients, starts from 0 point, learn how to cook, and then have this like uncertainty that he might fail, he might burn his food, or he just can go to the fast food restaurant and buy his meal and consume it, and that's it. So it is all due to the funding, all due to the investment, and also to the enhancement that can happen in drilling and that can eventually lower the costs. I'm thankful for this question.
Yeah, super, thanks.
Okay.
Thank you, Abdi. Maybe now we can stop the recording.